theory. So what I will do is the following. I will apply results on modular forms to study 4-point conformal blocks on sphere of a two-dimensional conformal field theory. And if I still have time, I'll also say something about the application to the counting of flux vacua. So this is based on work in progress with Greg Moore and Nathalie Paquette, who is a very bright graduate student from Stanford who will be looking for a postdoc job this fall. So let's start with the first, with the introduction. So let's recall that modular forms are functions with special symmetries. For instance, we are familiar with modular forms defined on the upper half plane. And a familiar example of such a modular form is the so-called J function, which is invariant under SO2Z, as you can see from this picture. Well, however, more generally, modular forms have a slightly more complicated transformation. It transforms with a weight. And the way to think about it, to understand it, is probably to understand modular forms via the definition of lattices. How it works is the following. For a given point on the upper half plane, you can associate to it a two-dimensional lattice generated by the identity vector and the vector tau. So in such a way, a modular form can be thought of as a function associated to each 2D lattice C number. It's a wrong kind of error here, I apologize. Well, okay, and this function, if it has to be a modular form, it definitely have to satisfy the following scaling relation. Namely, if you rescale the size of the lattice by a number lambda, then the function should rescale in this way. And this number k is called the weight of the modular form. Well, we all know that modular forms on the upper half plane have a lot of applications, and the best way to understand it is to think about modular forms in terms of a torus. So how it works is that we focus on one fundamental domain of this lattice and identify the sides, and in this way we get the torus. And this generator tau will now become the complex structure of this torus get. And the applications that came out from this is very numerous, and namely, mostly in the domain of 2D CFT. For instance, we have the Cardy formula for the growth of states, and we have the classification of CFT based on the methods of modular forms. But we also, via ADS CFT, we can explain the counting of statistical entropy of black holes and have bounds on holographic theories and so on and so forth. And if now we place this torus not in the world sheet but in the space-time, then we have applications, for instance, to the topological string amplitudes that we have also heard just from Murad just now. Okay, so that's the story so far, and in the rest of the talk, I will describe a few generalizations of this story. So the first part, sphere conformal blocks. And if you're planning to take a nap in the following 10 minutes, the takeaway message is forget crossing. Everything is just modular. And this is based on the work in progress with Terry Gannon and with Guillermo Lockhart. So to study a 4-point sphere block, well, let's first look at the underlying moduli space. And we're all familiar with the fact that using SO2C, we can map 4 points on the sphere to these 4 points, 0, 1, infinity, and an arbitrary point Z on the sphere. As a result, the moduli space we want to deal with is a sphere with these 3 points removed and parametrized by this cross ratio Z of the 4 points. So after knowing the moduli space, we want to know the symmetry of the sphere with 4 punctures. And the symmetry group clearly is closely related to the spherical pure braid group of 4 strands. And the adjective spherical just means that we keep track of the fact that the endpoints of the strands live on the sphere, and hence this kind of braid we can simply unwind. And pure just refers to the fact that we take the 4 points to be distinguished, and hence we do not allow permutation of the marked points. So if you look at this group, it turns out that up to Z2 identification, this is nothing but gamma 2, which is a simple subgroup of SO2Z, and which consists of elements of SO2Z that are identity mod 2. So we get to the conclusion that the symmetry group of a sphere with 4 mark points acts naturally on the upper half plane. So we would like to know how it acts. And we will know how it acts if we are provided with a map from that associates to each sphere with 4 mark points a torus. And there's a canonical way to do that. Namely, we take 2 sheets of such a sphere and connect it, then we get a hyperelliptic surface that is nothing but a torus. And if we use the uniformizing coordinates on the torus, we will get that the complex structure of this torus is given by this function in terms of z, or in fact the inverse of it. Indeed, this map is invertible. It actually provides an isomorphism from this moduli space that we have seen, namely a sphere with 3 points removed, to the fundamental domain of gamma 2. And indeed, this in particular is invariant under gamma 2. And the 3 cusps of the fundamental domain just corresponds to the 3 different ways that a sphere with 4 mark points can degenerate. Okay, now we have the map. We can figure out the action of the group. So if you translate between gamma 2 and a mapping class group, you'll get the following simple picture, namely the 2 generators of gamma 2 simply corresponds to the 2 generators of the monodromies on the sphere with 4 punctures. So that's simple. And indeed, if you work with a full spherical braid group, namely you forget for a second that the points are distinguished, and you'll see that SO2Z, the full modular group, is the subgroup that fixes 1 point and allows for a permutation of the 3 other points. So, okay, so far everything is very simple. We can ask, does this gamma 2 have a bit of more interesting representations? And it is well known that conformal blocks of a chiral CFT furnish representations of the mapping class group. And indeed, on this picture, on the, we have 4 insertions on the 4 mark points, and the monodromy translates into exchanging, rotating these 2 legs and rotating these 2 legs. So we get the conclusion that 4-point conformal blocks are functions, furnish representations of gamma 2. And so in other words, they are modular forms. So what type of modular forms they are? Well, it's also known, the answer is also known, because we know what these moves do to conformal blocks. For instance, they transform into each other via fusing and braiding, famously. For instance, if we act on it with a braiding, we exchange I2 and I3, and with a mixture of different internal operators. And if we do it twice, we got one of the monodromies that we have just seen before. And namely, the conformal blocks are vector value modular forms for gamma 2, by definition. So the dictionary between the usual CFT language and modular form language is the following. So the number of the allowed internal operators inserted is the size of the vector. Well, or in general, it will be given by this fusion combination of the fusion numbers if it's non-trivial, if it's not just 1 or 0. And different, but let's assume it's 1 or 0 from now on without much loss of generality. And the different internal operators correspond to different components of the vector, at least in this preferred basis. And the fusing and braiding is nothing but the modular property of these vector value modular forms. And remember the fact that if we like SO2Z better than gamma 2, and we have to allow for permutation of 3 of the 4 points. So it just says that once you have at least 3 of the 4 insertions being identical, then you have enhanced modular symmetry. Namely, your blocks are vector value modular forms for SO2Z with precisely the same kind of dictionary working. So that all sounds fine. So how does it look in practice? Well, let's start with the most simplest example. The Ising model. We know what their conformal blocks are in terms of the z variable, the cross ratio. Now let's write it in terms of the modular forms. And these are just given by simple ratios of products of the data gain eta function. So for instance, here I'm looking at the sigma conformal blocks, and they're just 2 allowed internal insertion, namely the identity and the epsilon. And then, as I said, from the braiding and fusing and the fact that all 4 insertions are identical, these have to be vector value modular forms under SO2Z. And in fact, this is, if you open your modular form dictionary, this is the unique, well, up to a trivial rescaling, of course, unique 2-dimensional vector value modular forms for SO2Z with this singular term, which is just given by nothing but the conformal weights of these things. With this singular term and the S and T matrices determined by the fusing and braiding matrices. Well, so if you fix the singular term and the transformation matrices, you get this unique answer. But wait a second. Remember that usually we also see modular forms in CFT, namely the torus blocks are modular forms. And if you remember, these S and T matrices show up in the usual sense, namely as the S and T matrices of the torus blocks or the characters in another theory, namely the SU2 level 1 WZW model. And the central charge also work out. And due to the uniqueness, the answer has to be the same. And indeed, they are the same. These are the same functions. This coincidence happens not just for the Ising model, but more generally, there's a coincidence between conformal blocks and characters of 2 different theories. So now let's look at another example, which is more interesting from a representation theory point of view, but also extremely well known, namely the Liouville theory. So consider the Liouville theory. Now it's not a rational theory, but let's take one of the leg to be inserted by a degenerate operator. Then the number of allowed internal momenta truncates. In this case, there are just 2 allowed momenta, where alpha here is parameterized by Q at 2 plus P. And they famously satisfy some differential equations and famously given by the hypergeometric functions. So the equation expression in blue is what we're familiar with. And now you can start expanding it in the Q series in gray here. And here, well, from looking at the gray expression in terms of Q, we can read off clearly the T matrix here. And recall that for physical states, P is a purely imaginary number. So we see that we get a non-unitary representation of SO2Z in this case. And what about the S matrix? Well, the S matrix, you can also compute it, but it's actually very simple in this case because when you map from tau to minus 1 over tau, Z, the cross ratio just goes to 1 minus Z. And hence, the S matrix is given by nothing but the identity among hypergeometric functions. Okay, so these are conformal blocks. But now you can also put conformal blocks together into 4-point correlators. And now, clearly, they have to be invariant under this monodromy because we have the chiral and anti-chiral part. And they also have to satisfy crossing symmetries. So you get this statement that 4-point correlators with 3 identical insertions are SO2Z invariant. That is the statement of the crossing symmetry. Of course, there's also an analogous statement when you have non-identical insertions. Okay, so let me actually conclude this part now. What we've learned in one sentence is just that 4-point sphere conformal blocks are modular forms. And in some sense, what we're doing is we're just filling a page in your favorite CFT review. First, in the sense that it's such a simple story, it could all have been fleshed out 20 years ago. And second, we believe that this is a very natural and potentially much more efficient way to describe 4-point conformal blocks, and hence it probably should have been probably included in my CFD lecture notes next time. And abstractly, you get a funny statement here, because as we have heard yesterday from Inxin's talk, CFTs, at least rational CFTs, are completely specified by the fusing and braiding of the 4-point conformal blocks as well as the S matrices of the torus blocks. But now I'm telling you that forget fusing and braiding, it's also just S and T matrices. So everything is, everything in principle, everything about rational CFT are encoded in terms of modular data of modular forms defined on the upper half plane. And the third thing I want to mention now is that properties of modular forms, they correspond to they correspond to non-perturbative information about the blocks, so much more powerful than your usual Z expansion. Indeed, we can think of many applications here. Well, because we know so much about modular forms on the upper half plane, so we should be able to use them to compute the blocks and constrain the spectrum. And these tools include, it's a very incomplete list, but a very well controlled space of possibilities. Usually these spaces are really low dimensional. We have seen a case where it's one dimensional. And there's also classifications of low dimensional representations of SO2Zs up to, I think, 6 or 7. And we have Rademacher sums, which is very powerful numerically. And note that our discussion does not restrict ourselves to Virasoro blocks. Indeed, when you have a extended chiral algebra is where we think we can get new results, where we can get new results instead of just reproducing old results. And another thing is, well, in this sense, all bootstrap is modular bootstrap in 2D CFT. And well, for instance, these structure constants that sit inside the correlators are pretty hard to get. And what one can start doing is to start using the modular form techniques, because this problem, namely to combine the chiral and anti-chiral part into something invariant, is what we're very familiar with, namely how to combine the characters into a modular invariant partition function. For instance, in the Ising model case, this is going to be equal to the partition function of the SU2 level 1 WZW model for the reason that I just described. And future directions, first we see a relation also between sphere 4-point conformal blocks of one theory and the torus blocks of the other theory, which is something that deserves to be understood better. And second, it will be interesting to explore the holographic manifestation of this fact. And this is the, oh yeah, last but not least, we have learned that our friends at McGill, including Alex Maloney, Henry Maxfield, and Jing Xing, are also thinking about somewhat related subjects, so we're interested in learning what their point of view is. So this is the end of the first part of my talk. So how many minutes I still have?
You have 5 minutes left.
5 minutes left, that's plenty. Okay. So in the second part of my talk, we will apply results on modular forms to take you for a very quick stroll in a corner of the landscape. So the mathematical result we want to use is the following. So we have heard a lot about modular forms on the upper half plane, which is the same as this space when n equals to 1. But what about modular forms defined on this space with higher n? Well, these modular forms are supposedly important mathematically, for instance, for the study of Lennon's program, Lennon's conjecture. So, but there is much less is known about these modular forms, but we have this growth formula that applies very generally to these guys, which says that the dimensional modular form of this group grows polynomially with the weight. And to make sense, to use this formula, sometimes we do need to know the prefactor, hence this is given by the volume of the fundamental domain of this group. And if this group gamma is the isometry group of lattices, then using the lattice data, this formula has been derived to express its volume. So why do we care? Let's go back to the problem of counting flux vacua. Under some technical assumptions, here you're not supposed to read the small print, but this is the formula that Ashok and Douglas gave us. There are two factors. The first factor is nothing but the ball in the volume of a ball in the flux space. So it's just counting the lattice point in a ball. And the maximal allowed number of fluxes is given by the tadpole cancellation in terms of the Euler character of the fourfold in the orientifold picture. And the second factor is a factor that depends on the geometry of the moduli space. And this factor is closely related to the volume of the Calabi-Yau moduli space, which is something we know very little about. For instance, inspired by this formula, there has been results on the finiteness of this volume, so we know it's finite. But what is the number? We have no clue. So as a result, this factor is usually almost always ignored in the estimates of the number of flux vacua. But we know that now that the volume can be very, very small. For instance, there was a paper by Greg Moore last year, computing the moduli space, the space volume for K3, and that's 10 to the 60 in his normalization. So minus 60, yes, minus 60, sorry. So now we would like to know if in some cases, we can estimate this factor. So indeed, moduli spaces of some Calabi-Yaus, including various self-mirror quotients of K3 times T2 and T2 times T2 times T2 are of this form. So now we can compute its volume, so we're very curious what the tally will turn out to be. So let's, for the presentation, focus on just the simplest example, the Enriquez Calabi-Yau. And we know the exact complex structure moduli space. So let's now go back to the lattice formula and try to compute it. This is basically the result. So this factor with all the factorial and powers of pi and 2 included turned out to be of order 10 to the minus 8, which is not so small. Well, the main difference between this and 10 to the minus 60 is because normalization. There it's the Zamolodchikov metric. Here is the Weil-Peterson metric. And how about the first part? Well, the first part, we can't say explicitly what because we don't know the fourfold. But the fourfold is presumably very closely related to K3 times K3. And if we take that as an order of magnitude estimate, this is the first factor, 10 to the 10, 20, something like that. So we might say that the geometric factor seems to have a non-trivial effect. But this is just one example. And is it possible to say something more generic at all? Well, without going to the details, the geometric factor have the tendency to increase exponentially, at least in this type of Calabi-Yau, with the dimension of the moduli space. But the first factor, remember, also is expected to increase exponentially with this Hutch number. So maybe there could be a subtle balancing effect. We don't know. I mean, but this is a possibility just by looking at the plot. And so that's a very quick summary of what we have done. And clearly there are many open questions. For instance, the biggest question is just how generic it is, because these are quite special Calabi-Yaus. And so it should be possible to try to get more examples. And is there any physical role in these p-adic lattices that we have seen that has enabled us to compute the volume? And finally, the physical role of the moduli space, of the modular forms on these moduli spaces. Usually these modular forms play an interesting role in physics, but here we don't know the answer yet. So here is the end of my talk. Thank you very much.
So the calculation of four-point function reminded me of calculation of twist fields where you basically compute both.
Yeah.
Actually, that might even just be exactly what you need to understand the four-point function of sigma, right?
Of sigma. Oh, you mean of the Ising model example? Yeah, probably. Yeah. Here I even have like a
because you're just computing on the cover.
Remark that, of course, we thought about it and think that the modular form story is, in general, much more general. But in that example, I agree. I completely agree. You mean by using the hyperelliptic picture?
I don't understand. That's c equals to half. She's getting c equals to 1. Two different theories.
I know.
These are different theories.
Yeah,
but
I was just saying that sort of reminds me of. I think
there's an identity. I don't think there's the same thing.
well, yeah, but okay. So twist field story, as you told us, it should be related to the symmetric products of the. You mean the relation to the partition?
No, this observation that you made is in our paper with Hamidi about computation of twist fields.
Mm-hmm.
And we relate it exactly to the modular forms.
Right, you mean the Ising model?
No, in general.
Mm-hmm.
We formulated 4-point twist functions to the partition function of elliptic curves. That was the formulation in all days we used that already. This fact that you were mentioning as a fact is something that we actually used in our paper with Hamidi.
Yeah, but
we didn't have any connection between conformal theories. That's a new point you're bringing up. The connection with torus was already important for computation of twist.
That I understand in that picture. But we're saying like no matter what, I mean, forget about the connection to other theories. We can always write such a thing. Yeah.
But there's one point I didn't understand. You mentioned the modularity as a transformation is clear, but there's more than that in the modular form. There are integralities. there's no integrality naturally from the conformal block. At least you didn't connect that. That's the
No.
crucial point.
No. But I mean, not all the modular forms have integral coefficients either.
Yeah,
No,
So
but
you
that's,
can-
if you were trying to find a bootstrap to the modularity like Ian was talking,
Yeah.
for him, integrality is crucial.
Yeah.
It's a crucial ingredient, whether he used it or not, I don't know, but it's a crucial fact about those characters. Whereas maybe it's true also for you, I don't know. Have you checked it? It's always you get an integral structure or not?
No.
You haven't checked it or you don't get?
It's not always integral.
Oh, it's not integral. So there's no isomorphism between these two questions.
It's not always integral.
So this does not always map any CFT to another CFT.
Yeah.
There are
No,
cases
we
where-
are not making that claim. We just have a bunch of observations that can probably be explained somehow via
so
ingredients
you
that we
also
already know.
have examples. That's
Yeah,
I
yeah,
see.
yeah. Yeah, we don't have a prediction of this to that CFT.
So
but-
is it true that for rational conformity theories, the 4-point functions give rise to another conformity theory, or even that's not true?
that we don't know. That could
I mean,
as
you
well
only
be
deal with
true.
stuff which is non-rational. If you
Right.
just restrict to rational, like WCW
Right.
theory, this and that,
Right.
do you know what this map gives you?
No. We have a bunch of data with some pattern, with some structure in it. And for instance, for all the characters of we check first the things that are easy to check. For instance, when you have two-dimensional representation, and the list of WZW models that give rise to those are classified. And for those, we can find the minimal model, corresponding Virasoro minimal models with the corresponding 4 blocks. There's
What are your thoughts on physical interpretation of this Kurzweil formula?
I'm just showing this formula for the rest of the people. Well, of course, it's an extremely important formula, and thanks to this formula, there are these results. And yeah, and as I said, I think modular forms defined on these spaces on these moduli spaces should play a role in the compactification, in the corresponding compactification. But this is in large weight limit, so I don't know what I should do in physics. So the short answer is I don't know. It's a nice formula. Yeah. Because for instance, like modular forms on other moduli spaces, for instance, on the upper half plane when you have the torus, or in some sense, if you take n equals 3, then you have a single upper half plane, then that's in some sense the moduli space of the n equals 4 compactification. And as Robert and company told us, that counts the black holes in that. So that's sort of the physical implications that I had in mind when I raised that open question. But yeah, the dimension of this, I don't know exactly whether that should play, this exact object, whether that should play an important role, I don't know. Would be nice, of course.